Introduce Doug Erwin. Hello, Doug. I'm very happy. It's also early morning, but not so early as with stars, 7 o'clock or something, right? Doug actually wanted to come, but was prevented, and so he's giving this lecture on Zoom. And Doug is a paleobiologist who worked for many, many years or decades at the Smithsonian Museum of Natural History, and he was retired recently and is now at the Santa Fe Institute for Study of Complex Systems. This is correct, right?
Right.
Okay, and Doug, you have been mentioned several times today or yesterday for your collaboration with Eric Davidson and the papers you wrote with him on evolutionary biology. So, the floor is yours. I'm going.
Thanks very much. I'm very sorry that it didn't work out for me to be there with you. I've listened to the last few talks on chemistry, which were fascinating, and I know that I would have really benefited from being there the last few days, but that turned out not to be possible. So rather than talk about either evolution or the work that I did with Eric, I thought I would go back to my disciplinary foundation, which is in geology, and talk about two events that happened in the latter half of the 20th century that fundamentally changed geology, but in different ways. And the first of these, of course, is the plate tectonic revolution. And the second, which has, I think, both similarities and differences from plate tectonics, was the Alvarez impact hypothesis for the end of the end Cretaceous mass extinction. Let me see how there we go. So most of you, I'm sure, are aware of the concepts of plate tectonics. This is the idea that the Earth is divided up into some large lithospheric plates which float on a molten mantle. The plates move because of seafloor spreading along mid-ocean ridges primarily, and then there's subduction beneath areas primarily around what's called the Ring of Fire around the Pacific, but also in the Mediterranean and most of the other oceans. And this dynamic process means that the continents are much older than the oceans. The oceans are continuously being rebuilt by this activity of seafloor spreading. This idea of plate tectonics, of course, begins with, usually its thoughts begin with the German climatologist and geologist Alfred Wegener, who proposed the idea of continental drift first in 1912, and then wrote a book on the continents and the oceans in 1915, and then multiple later editions before he finally died on the ice in Greenland in 1930. And the book continues to be fascinating, at least in the English versions, which I can read rather than the German, because he was not talking just about the similarity in the fit between the continents across the Atlantic Ocean, particularly between Africa and South America, but was also talking about similarities in rock types, and he even speculated about ideas of spreading and tried to provide a mechanism. Now, Wegener was not the first person to think about continental drift. The ideas actually go back to about the 1590s, and other geologists had speculated about that. But Wegener provided the first sort of comprehensive ideas about this. And that from the time that he wrote up through the 1950s, there's an ongoing sort of low-level discussion about ideas of continental drift. Most of those were sort of the difficulty was that there was no obvious mechanism, and geophysicists in particular ridiculed the idea of continental drift because of the idea that there was, these continents were somehow plowing through oceanic crust, which they thought was completely absurd. I want to mention a South African geologist, Alexander Dutoit. He was an ardent supporter of Wegener and continental drift. He did extensive field work both in South Africa and also in South America, and he generated, particularly during the 1930s and into the 1940s, considerable evidence of the similarity both in the geology and the fossils between South Africa and South America. This is important because when I first started working in South Africa in Namibia in the 1990s, I talked to a number of older geologists, and they pointed out that Southern Hemisphere geologists had basically accepted the ideas of continental drift long before they were accepted in America and in Europe. And partly that was because to them the evidence from the supercontinent that we call Gondwana now, with the unification of South Africa, South America, Australia, and some other continental pieces, was so obvious that even in the absence of a mechanism, that didn't dissuade them from the ideas of what Dutoit called the wandering continents. And particularly in the U.S. and to some extent in Europe, that acceptance was really impeded by the lack of a mechanism. So this is some of the evidence that both Wegener and particularly Dutoit identified, showing similarities in fossils, similarities in a variety of different geology, rock types, and mountain beds as well. So what were a number of people have talked about the idea of an impending crisis being necessary for revolutions and a revolution wiping away previous ideas. The leading previous view of geology is what was called geosynclinal theory. Marshall Kay in 1948 published a very well-known book in which he described the geosynclinal theory. This is a cross-section through the eastern part of the United States with eastern New York, Vermont, New Hampshire, and then off into the Atlantic Ocean on the right side of this diagram. And you'll see a number of things labeled there: a myogeosyncline, a geanticline, and a eugeosyncline. Geosynclinal theory was predicated upon these packages of sedimentary rock, particularly myogeosynclines and eugeosynclines. The eugeosynclines being deeper water rocks. And these were thought to be the foundations upon which subsequent mountain building activity were based. But as one quip pointed out, the problem with geosynclinal theory was that it was a theory of mountains with the mountains left out. And by that, the quip meant that there was no mechanism by which these packages of sedimentary rock were uplifted to form, in this case, the Appalachian mountain belt, which is where the geanticline is shown, and then also parts of the eugeosyncline. But this was the major theory. There were two other competing theories that I should mention, or allied theories. One was the way paleontologists dealt with this fossil evidence was by constructing land bridges that united places that were needed to allow animals and plants to move between, say, South America and Africa, in order to explain why monkeys live in South America, for example. And the third option was what's called the expanding Earth hypothesis, which was the idea that the Earth had actually been getting larger over time. And that, even into the 1980s, there were a lot of people who felt that explained a lot of geological data better than anything else did. So these ideas of geosynclines and whatever persisted through the 1940s and 50s and into the 1960s. They began to break down in the 50s, however, with the ability to start mapping the oceans. This is a very famous map. This is from the Library of Congress in the U.S. that was constructed at Columbia's Lamont Doherty Laboratory by Bruce Heason and Ray Tharp, and the artist was Bernan. This is a depiction of what the oceans would look like if you stripped out all the water. So if this was Mars with the continents and then the oceans, and you can see the prominent mid-ocean ridges going through the Atlantic into the Indian Ocean and across into the Pacific. There's a significant problem with this map, which was that Ray Tharp in particular, who was responsible for most of the cartography, was very fixated on what was known about the structure of the North Atlantic mid-ocean ridge, and basically applied that structure to the rest of the mid-ocean ridges. The problem is that the North Atlantic mid-ocean ridge spreading center, as we now know it, is much slower than what's happening in the Pacific. So consequently, the mid-ocean ridge is higher in the Atlantic than it is in the Pacific, where the spreading rates are considerably higher. But this evidence that was presented about mid-ocean ridges was one of the significant pieces that led to the plate tectonic revolution beginning in the early 1960s. In 1962 or 3, there was evidence from magnetic anomalies across the North Atlantic and also evidence from the Northeast Pacific. This was produced by towed arrays from ships that were recording magnetic signatures. You can see in the figure on the right a cross-section across a ridge axis in the center, and there's this pattern of magnetic positive and negatives, which is explained by the reversal of the Earth's magnetic field. And eventually, Fred Vine, who was a student at Cambridge, started thinking about this actually as an undergraduate, believe it or not, and put together a paper arguing that this was a mirror image of anomalies on either side of the spreading ridge, and could only be explained if the ridge was being created during times of one magnetic polarity and then moving apart. As you see in the lower figure, the lithosphere is moving to the side, and these positive and negative anomalies with mirror images or mirror symmetry are produced that way. The same idea, they submitted this to Nature, I think in 1963. The same idea had been proposed by a Canadian geologist named Morley 6 months earlier, and his paper was rejected by Nature. But today, geologists know this as the Vine-Matthews-Morley hypothesis. And if you look at this from a global perspective, you see in this image these large lithospheric plates and a number of smaller plates with movement away from these mid-ocean ridge spreading centers. You can also see here in North America, if you can see my the arrow here, this is the San Andreas Fault, which is what's called a transform fault. The idea of transform faults were introduced by a man named J. Tuzo Wilson in about 1965 in a series of papers that he wrote. And eventually, as I'll show in a minute or so, these ideas coalesced through the 1960s into this idea of plate tectonics. This is, I wanted to add a little bit of color. This is a figure from a talk that Paul Hoffman, who was at Harvard for many years and then at the Geological Survey of Canada, did in 1986, showing the various plates that comprise North America. The different colors indicate the different ages, as you see on the right. The important part of this is that what Paul did in his work was show, particularly by looking at what's called the U.S.A. orogeny, which is up in the northwest part of Canada next to Alaska, that plate tectonics had been operating for at least 2 billion years. And he and his students showed that the U.S.A. origin was geologically essentially identical to much more modern orogenic episodes. This figure shows the ages of the oceanic crust, as shown on the bottom. The red is the most recent crust, and then you can see it gets progressively older as you move away from the spreading centers, and then it's subducted below various continents along subduction zones, which is what is shown in this figure with a more modern view of these major tectonic plates dominated by the huge Pacific plate and the Pacific Ocean, and then also the large North American plate. But there are a number of smaller plates. This is about 15 or 20 years old. I particularly like this figure here because in brown, this represents sort of the next generation of plate tectonic theory, with the idea that there are actually fairly diffuse boundaries between many of the tectonic plates. Rather than a sharp break at a subduction zone or a transform fault or a spreading center, the brown colors here show these diffuse boundary zones, the East African Rift, the Cordillera of South America, most of the western United States, for example, large parts of Central and Southeast Asia, because of very dynamic activities through these areas. This is an interestingly different view of plate tectonics than I got when I was in graduate school, where these plates were thought to be much more rigid and less diffuse at their boundaries. So this is a timeline of the plate tectonic revolution with Wegener in 1912. A number of geologists expanding on elements of the ideas of continental drift from the 1920s into the 1950s, but as I've said, this idea was not widely accepted by geologists and was essentially disparaged. And in fact, in the 1940s, one of the questions, late 1940s, one of the questions on the Cambridge geology exam for seniors was to explain what was wrong with the idea of continental drift. So in 1962, Howard Hess, Captain Hess, formerly of the U.S. Navy, then at Princeton, presents the idea of seafloor spreading. The Vine-Matthews-Morley hypothesis uses paleomagnetic evidence, particularly from the group led by Keith Runcorn in Cambridge, to produce this idea of spreading centers, or to elaborate on Hess's idea of seafloor spreading. J. Tuzo Wilson introduces transform faults in the Wilson cycle in the mid-60s. And then in 1967, there were a series of papers given at the American Geophysical Union and published later that year, presenting mathematical models of plate motion. And this is really the solidification of the idea of the theory of plate tectonics. And one of my advisors when I was in graduate school, Tanya Atwater, was a student at Scripps in 1967 or 68. And I took a graduate tectonic seminar from she and Bruce Leindijk in graduate school, and she wanted us to learn three-dimensional spherical geometry, which I didn't want to learn. And I discovered that I could get her talking about the history of plate tectonics and thus avoid having to do three-dimensional spherical geometry. one of the stories that she told us was about sitting in a graduate seminar at Scripps in 1967. And the seminar was on plate tectonics. They were using Marshall Kay's book, and an issue of the American Geophysical Union Journal came out with these papers by Morgan and Mackenzie, and they literally tore up the geosynclinal syllabus that they were using and started doing plate tectonics. It was that obvious to them at that point that these previous ideas had little relevance moving forward, and Tanya actually became one of the first generation of people working on plate tectonics. So, from my view, these ideas about plate tectonics were a true paradigm shift in the Kuhnian sense. They eliminated a whole variety of research programs across geology. They preserved the sort of core of what field geologists were doing, but they provided a completely different way of looking at the dynamics of the Earth. But one of the interesting things about the plate tectonic revolution is how there was no single figure that you really can point to as a key revolutionary. It's rather a community-led effort, but it was a community, as the last point here, I want to emphasize, it was in some ways a very small community. It was really MIT and the Woods Hole Oceanographic Institute, Scripps, both of which had ships, so they were getting a lot of the data on what was happening in the oceans. People at Cambridge, at Columbia, Lamont Doherty, and in Paris. So students outside, exactly outside that relatively small number of institutions, had much less immediate access to these ideas about plate tectonics. And as many many American geologists know, Harvard wouldn't sort of agree that plate tectonics was not a passing fad until well into the 1980s. But that meant that the adoption of plate tectonic theory was very uneven across parts of Europe and North America, while the people in the Southern Hemisphere were going, what took you so long? We knew this was going on for decades. But one of the key drivers of this revolution was the fact that the plate tectonic theory, because of seafloor spreading, because of the ideas of rigid plates and the understanding of subduction, provided a firmer mechanistic foundation than Wegener's idea of continental drift or the ideas that were prominent from the 20s into the 1950s. And the whole idea of plate tectonics has continued to be fruitful across all of geology. So essentially there is no part of geology that has not been touched by plate tectonic theory. That includes how we look at biogeography and paleontology, geochemistry. It sort of doesn't matter. Everything has been changed by the idea of plate tectonics, even though the adoption of plate tectonic theory took quite a while. When I was a TA in the early 1980s at UC Santa Barbara, one of my advisors was still teaching historical geology with my geosynclines because he'd gone to Harvard and didn't understand plate tectonics. And we finally fired him for a week of the course and told him to go away and go to do something else, because the TAs were spending so much time having to explain how geosynclines and plate tectonics work together, that it was just taking up too much of our time. So we told Stan to go away for a week, and we taught the course with plate tectonics and got rid of geosynclinal theory entirely. The second revolution that I want to mention is the idea of that an impact caused the extinction of the dinosaurs 66 million years ago at the end of the Cretaceous. Again, most of you will be familiar with the outlines of this theory. And here what I want to emphasize, and I expect that Udi will reject this as a scientific revolution as soon as we get to the discussions, because in many ways, unlike plate tectonics, this didn't fundamentally change what anybody did. It certainly led to a resurgence of interest in mass extinctions in general, not just in the end Cretaceous mass extinction. It brought a lot of non-geologists, particularly physicists and others, into looking at this event and to some extent at other geological events. So it increased synthesis, but it really was essentially a conceptual revolution in that it expanded the realm of processes that geologists could think about or were allowed to think about. So the interesting thing about this idea is that for 150 years, ideas of catastrophism had been banished from geology. When Charles Lyell wrote his books on geology in the 1830s, many of them were directed against catastrophic, what was called catastrophism in the late 18th and early 19th century. Lyell tried to banish those ideas of catastrophism and was largely successful in doing so. So that there was 150 years of training in geology in which you didn't think about extraterrestrial causes, you didn't think about catastrophic explanations for geological, as a geological mechanism. And what the Alvarez hypothesis did was make that, in a sense, a reasonable thing to do given sufficient evidence. So this paper was published in 1980 in Science, Extraterrestrial Cause for the Cretaceous Tertiary Extinction. And I have a quote here from the abstract, which describes the basics of the idea that there was a large impact that happened at the end of the Cretaceous. The evidence for that came from enrichment of platinum group elements found at Cretaceous tertiary boundary sites. They had 3 different sites that they looked at, Gubbio in Italy, in Denmark, and one other in this initial paper. This is a section from pelagic limestones in Gubbio, which is shown on the right. And this shows that the KT boundary, there's a large increase in the amount of iridium in the clay fraction in these limestones. And they, in this paper, say that the only plausible explanation for this increase in iridium is the collision of a comet or an asteroid, which is bringing in this element and marking the KT boundary. Now, this Alvarez Sr. was a physicist who was prominent in the Manhattan Project during the Second World War. To say that he had a big ego would be an understatement. His son was a geologist and had been trying to figure out how to estimate sedimentation rates, and his father had suggested that the influx of extraterrestrial platinum group elements should be relatively constant through time, so that he could use this variation in the amount of iridium as a way of estimating how sedimentation rates were changing over time. When they found this spike, they were not expecting to find evidence of an impact. They were looking for something completely different. But certainly Alvarez Sr., it was obvious that this was due to an impact, and he certainly expected all geologists to thank him profusely for providing this new way of looking at the Earth. the problem was that there were a number of unanswered difficulties raised by this idea. The first was that for paleontologists, the fossil record at the time suggested not a catastrophic event, but rather a gradual one, so that even if there had been an impact, it wasn't clear that that was really the primary cause of the mass extinction. The second, which was immediately pointed out by sedimentologists and geochemists, was that there was actually little known about the behavior of iridium or other platinum group elements in the sediments. So, is it possible that this concentration and enhancement was simply a diagenetic process that happened with the movement of iridium through the sediments, and rather than being a primary signal? And in fact, later on, it was shown that microbes actually could concentrate iridium. So that was a second question. A third question was that even if there was an impact, were the climatic or environmental consequences sufficient to actually cause an extinction of the magnitude that was observed? And many people, and a few people even today, favor a volcanic cause for the end Cretaceous extinction tied to the Deccan traps in India, which turned out to actually predate the impact. But most importantly was that geologists had this 150 years worth of training that you didn't explain things with these catastrophic mechanisms that were proposed by the algorithm hypothesis. And that's what is really the key change that developed through the 1980s, was the recognition that there had in fact been this massive impact that hit the Yucatan Peninsula, and today we view as the primary cause of the Permian mass extinction. This sort of rejection of catastrophic explanations was turned on its head about 4 years later, when Gene Shoemaker, who was a U.S. geologist, part of the Apollo program, and had trained many astronauts in geology before they went to the moon, had become an expert on impacts because he was based in Flagstaff and had done a lot of work on Meteor Crater. And he wrote a paper in 1984 in which he pointed out that in fact the collision of extraterrestrial objects with the Earth was actually what we call a uniformitarian process. We should expect those sorts of impacts to happen with some frequency over time. And so Shoemaker sort of flipped the whole rejection of catastrophism on its head to say, yeah, there are external causes. Certainly we knew that impacts occurred. Looking at the moon, you know that impacts, there are a lot of extraterrestrial objects. And so Shoemaker's paper caused a lot of geologists to sort of rethink how willing they were to consider these sort of extraterrestrial explanations. The paleontological objections caused paleontologists to rethink what we actually knew about the fossil record. And Phil Signer and Jerry Lips wrote a paper in 1992 in which they pointed out that because of preservational biases, even a rapid extinction, a catastrophic event, will appear gradual in the fossil record because the least abundant taxa will have the fewest occurrences in the fossil record, and so they'll disappear well before the actual extinction of that particular taxon. So the lower the abundance, the earlier those things disappear, and the greater the Signer-Lips effect. And then Charles Marshall, a couple of years later, and then a number of other geologists, developed statistical techniques to account for the Signer-Lips effect, so that we could actually test for whether an apparently gradual signal was actually consistent with a catastrophic extinction. So there's a variety of different components to this KT impact hypothesis. And despite the views of the Alvarezes, there was quite a lot unexplained by the initial paper in 1980, but it was a very fruitful hypothesis. It caused geologists to rethink a lot of what they thought they knew about the dynamics of the Earth. And it led to a whole series of research programs and meetings through the 1980s into the 1990s, examining essentially every aspect of this hypothesis, from the size of the impactor, the length of the snowball winter. It led to the paper by Carl Sagan and others on the effects of large-scale nuclear bombs. It led to
Doug, you are almost finished.
I know. I'm down to my last slide here.
Okay.
So these are two new paradigms, very different ways of looking at the Earth. And the main point I want to make here is the plate tectonic idea was a destructive revolution, in the sense that I think some of you have used that term, in that it eliminated wholesale most previous ways of looking at the dynamics of the Earth, whereas the last hypothesis about the snowball Earth was a much more conceptual reorientation that didn't actually change anything about how people did geology. And I'll stop there.
Okay, questions?
Hey, Doug. Evolutionary biology. You mentioned biogeography briefly, but the way we think about how lineage is split and things like that, can you comment on that?
Well, it's certainly underpinned, as you know, vicariance biogeographies, the idea that we could explain a lot of distributions of taxa by the splitting of the continents was a central part of the development of phylogenetic analysis and cladistics, which is happening at about the same time. That turned out to be probably overblown. Vicariance biogeography is sort of, the proponents of it tried to explain everything via that method and plate tectonics rather than looking at dispersal. I'm not sure how much it affected other aspects of evolution beyond biogeography. I think that was the major initial impact, but it certainly gave a different way of looking at the dynamics of evolution and the dynamics of dispersal.
Okay, thank you. Everybody. I have a question. Can you hear me?
Mm-hmm.
Okay. You called the plate tectonics theory Kuhnian revolution, and I wonder, it contradicts one major statement of Kuhn, namely that new paradigms should be random, they should be not inspired by rational thinking and so on. And you said that the plate tectonics theory is better than Alfred Wegener's theory because it provided a mechanistic explanation.
So what's interesting about Wegener is that he actually had the right explanation, but there was too little understanding of the structure of the Earth for his explanation of C4 spreading, essentially, to be viewed as viable at that time. So it wasn't until the oceanic explorations in the 1950s and the development of the Hesen and Thorpe map and other evidence, the paleomagnetic evidence that was coming in the 50s and 60s, that there was an empirical foundation to put under what he said. But note that even with the work that was done in the early 60s, it wasn't until 67 when the idea of these rigid plates was introduced by Dan McKenzie and Morgan, that that was the thing that I think flipped the switch for a lot of geologists, in that they were able to put a lot of this earlier evidence together in a coherent framework that would impact a lot of geology. So the Wegener certainly had pieces of it, as did others both before him and after, but they weren't, the idea of continental drift lacked the idea of the plates and the dynamics of the plates that was really essential, I think, to forming a coherent theory.
Okay, all right, so it was essentially better, and you could compare the two.
Yeah, and many people have. I mean, there's a whole.
Okay, no, that's what I say, and that is in contradistinction to what Kuhn said. So it was only a semi-Kuhnian revolution, right?
Yeah, or Kuhnian just was too focused on Copernicus and Newton.
Yeah,
Didn't
no,
look
we
or what?
will discuss it some other time. Okay, thank you. Anybody else? Then, Jack?
One question.
Yes?
Did the idea of catastrophism spread from geology to biology and evolutionaries?
Did you understand?
Yeah, I think it probably did. Although ideas of macroevolution, of rapid evolutionary change, were already fairly widespread among paleontologists long before the Alvarez hypothesis. But it certainly opened up a lot of conceptual opportunities for geologists to think about catastrophic explanations that had just been, I mean, you know, Geology 101, when you're an undergraduate, you learn that catastrophism is bad and uniformitarianism is good. That continues through your geological training, and the Alvarez hypothesis sort of eliminated that that way of looking at catastrophic explanations, certainly for geologists.
Okay, but to add something, you asked for biology. I think Doug was the first, or together with Eric Davidson, to show that uniformitarianism does not work in evolutionary theory for various reasons.
Yeah.
So, but it was not replaced by catastrophism. So, but it was by a different theory. So I want to thank Doug again for coming out of his bed so early and for giving us this interesting talk. So, and next time you come back you come back to Beersheba, I hope.
I hope so too. I'm very sorry I couldn't be there with you.
Okay, thank you so much. Bye bye.